So we shall now talk about two new important elements of a circuit. So unlike resistors, which only dissipate energy, capacitors and inductors ideally do not dissipate energy but store them, which, which can be retrieved at a later time. So a capacitor is a passive element designed to store energy in its electric field. So it is extensively used in electronics, communications, computers, and power systems. Examples, we have tuning circuits of radio receivers and dynamic memory elements in computer systems. A capacitor basically consists of two conducting plates separated by an insulator or a dielectric. We take a look at this figure right here. We have this plate and this plate, and it is separated by a dielectric with permittivity. So the capacitance is given by the permittivity of the material times the area. So this area, the area of the plate, over the distance between the two plates. This image shows some of the capacitors. So we have electrolytic, we have ceramic, we also have variable capacitor. So when a voltage source is connected to a capacitor, the source deposits a positive charge on one plane and a negative charge on the other. So as shown in this figure. So the capacitor stores the electric charge given by this equation. Q is equal to the capacitance times the voltage applied. So Q is equal to C times V. Now if you take a look at this equation right here, we get the derivative with respect to time. So we have dq over dt. So the rate of change of charge equivalent to C. So C is, remember C is constant. And then we have dv over dt. So we all know that the rate of change of charge is just equivalent to the current. The current in the capacitor is given by C dv dt, or C times the rate of change of the voltage. This equation shows if you have a change in voltage with respect to time, you have a current flowing through the capacitor. But if dv over dt equals to 0, meaning if the voltage is constant or is not changing with respect to time, I is just equivalent to 0. So there is no current flowing through the capacitor. Or if I is equal to 0, that means that the capacitor is equivalent to a open circuit. So following the passive sign convention, looking at these figures A and B, we have a voltage is polarity positive negative, and the current flowing entering through the positive terminals of the voltage. So we have I is equivalent to C dV C dV over dt. Now taking the voltage and current relationship, so we transpose dt and C to the other side. So we have dV equals to 1 over C I dt. So if you take the integral from both sides, we have Vt equal to 1 over C integral of I dt plus a constant k. Or we can set a definite integral of dt equal to 1 over c integral of I t prime dt prime. This integrated from t0 to the time t plus the initial voltage of the capacitor. And use this unit integral or definite integral. Now determining the energy stored in a capacitor. So to determine the energy stored in a capacitor, we begin with the power delivered to it. We have, remember, power is just equivalent to V times I. So substituting this equation, I right here. So we have dV times dV over dt. So transposing dt to the other side, so we have d dt equal to d v dv. Now if you integrate both sides and we evaluate this expression right here from v at t sub 0 to v at t, we have v prime dv prime. This is just equivalent to 1 half t. We have vt squared minus vt 0 squared. Now if you select the 0 energy reference at t naught, so this expression right here is equivalent to 0. In no initially stored energy, we have 1 half t squared. For example number 1, determine the voltage across a 2 microfarad capacitor if the current through it is 6e to the negative 3000 t milliamperes. So assume that the initial capacitor voltage is 0. So if we assume that our time not or initial time is equal to 0, so at v in our initial time is equal to 0. So using the equation, v equals to 1 over c integral of I dt. So plugging in the values, we have 1 over 2 times 10 to the power of negative 6 integral of 6e to the negative 3000 t dt. So this is times 10 to the power of negative 3 because this is in milli. So we have 3 times 10 to the power of 3 or negative 3000 e to the negative 3000 t. We have plus k here equivalent to negative e to the negative 3000 t plus k. So how do we find the value of k? There we are given this initial condition. So at t equals to 0 or v is 0, we have negative e to the 3000 times 0, we have 0 plus k. We have the value of k equal to 1. So our v is just equivalent to 1 minus e to the negative 3000 t volts. Or we can use the equation V equal to 1 over C integral of I dt prime evaluated from T naught to T plus the initial voltage. We have 1 over C 0 to T I dt plus V at T naught. So this is equivalent to 1 over 2 times 10 to the negative 6 integral of 6e negative 3000 t dt times 10 to the power of negative 3. We have negative e to negative 3000 t evaluated from 0 to t, which is just equivalent to 1 minus e to the negative 3000 t volts.